Okay, so welcome back. And I forgot to show you guys these pictures, but I actually added some pictures, just to give you guys a glimpse of how these things look like. So this is how moving average would look like. So the actual data that I have is this red lines. And what I have done is we take the average of these 3 data points, and I don't know, I don't think this is I think this is like not exactly the 3-point average, but yeah, they have taken some point average, and this blue line that you have is the average, moving average that you have. And if you plot the residuals, you get something like this, where you see that there is no pattern and the mean is constant at 0. So this looks like normal. And if you plot the histogram, you might be more confident in your classification of residuals as normal here. So these are the residuals after removing the trend that we have calculated. So, and then there was this next graph, which actually shows you, the sample autocorrelation function for white noise process. So this is how the graph would look like. And let's say if I have 20 data points, I know that if one of those, can exit. So at max, only one of these points can go beyond this interval that I have here. So this is the interval that I have, and all of the points are under this interval, and only one can go there. So this graph, this correlogram, tells us that the process that I am looking at is in actual, this process is in actual a white noise process. So this is the kind of graph that you will get once you use statistical softwares. And then this is the graph for correlogram of the moving average process. So you clearly see here that the black circles denote ACF. And we know that the ACF for MA process cuts off after Q, right? So here my Q is equal to 1. So I see that I have some ACF here, and then all the ACFs are just 0, right? And this is what your theory would predict. So these are the predictions by the theory. But of course, when you're having a real-time data at your hand, all of these values will not be exactly 0. But they will have to be, about or near 0. So you have some of these sample ACFs from the data that you have at hand, and these would be, likely to be around these values. So these aren't beyond the estimated prediction, the estimated confidence interval. I'm sorry, prediction interval is the wrong word and I shouldn't use that. So this is the confidence interval that I get, for my ACF. So remember the variance that I wrote for my MA series. In the previous case, it was something like 1 plus 2 and then summation of those rows. And that, so if you use that variance and if you figure out this confidence interval, so your data should lie within this value. And this is what you will get. So anything in between here is acceptable for this process to classify as the MA1 process. Is this clear? I hope this makes sense. Yeah. So now let us go back to the box Jenkins methodology that we will start with. So the very first step is to identify the model that we have at hand, right? So now we have yet seen how to identify a model which might be AR or which might be a pure MM process. But what can we do if we have something which is a non-stationary data? We've already seen methods to convert those data and to remove the trend and to remove the seasonality from the data. So again, I'm just writing this for the sake of completeness, that one thing that you can do is difference the data. So let us say always what you start with a broader idea, and then you eliminate the factors which you don't think are necessary. So you say that my model might be ARIMA, and I don't know what P, what D, or what Q as yet. And you start off with this, and you look at your data and see whether if it's a stationary series or not. And if it is stationary, well and good, you have your D as 0, because you do not have to integrate it, you do not have to differentiate to make it into a stationary one. It is already a stationary process. But if it is not, then voila, this is going to help you. And what you have to do is, there are certain things. So also remember, we discussed the ACF. If ACF directly cuts off to 0, then you know that it is kind of a stationary process. But if it doesn't, and if it is steadily declining from 1, then you know that if you difference that series, you are likely to get a stationary series. And then there's another concept which, can be used to determine the D. And I think this is actually a good exercise. So what happens is, let's say I have some process. So I have converted my process X using difference D times to Z. And to remember how many times I have differenced it, I'm just writing it as the power here. And what I do is I take the sample variance of this process. So now I'm taking the sample variance of this process. Again, when I'm talking about sample variance, I know that my variance should be as least as possible, because I do not want my model to vary a lot. I mean, if it is predicting the values which are farther away, that's no problem. But the prediction interval shouldn't be much wider, It could be narrower and still have a point which is farther away from the one that was in the last case. But the prediction interval should be narrower, not much wider, for us to, wander here and there about what possible value for the next time period could be the variable that we are taking into consideration. So what happens is, if you difference the data, you can plot a graph for how many times you have differenced the data and for the sample variance that you get. So let us denote the sample variance by sigma square D, which is what you will plot. And because it is the estimated one, we have this nice cute little hat up there. So what happens is, this is generally seen as a quadratic function. For the initial differences, it might decrease in value, but then there will come some point where it again starts to increase. And it has been proven that the one which minimizes the sigma square D, so in our case, it will be this D, the one which will minimize sigma hat square D. So this is what, so this D should be, the likely one that you should be used. And it could be 0, like if you have something like this, then it will be 0. Not exactly, sorry. If you have something like this, then it can be 0 or something else. So it clearly depends on, what kind of a time series you have at hand. So yeah, that's it. And I think there's a nice example, and I think we should go through this sum. So let me just share my book here. Yeah. Let us try to have a look at what this question is asking us to do. So we have the time series according to them, which is a monthly. So RPI here is the retail price index. You don't have to worry about if you don't know that economics. That's okay, but I am probably sure that all of you already know this. So it's good. And if you go to page number 152 of the tables, you will have this SACF. And R1, R2, R3, and R4 are given. So they're asking you to find an appropriate value for D in this case. So I think I hope all of you have your table booklets with you. If not, you can access the PDF as well. So if you go to page number 152, you will see something. I'll post a picture on the group maybe for you guys to have a look as well. So the part which I have marked are the ones that we have to, take into consideration. So what we are trying to do is, we have a summary statistics given on the page number 152 of our table booklet, and they have given us the values of R, which are what? The ACFs, right? These are the sample ACFs that we have, and we have to figure out the appropriate value of D. And we know how do we do that? We see what's the minimum value of sigma square D that these can take. So if you look at QT, I think, yeah, it's given right here. So if you look at QT, the standard deviation is 11.9. So the variance will be just the square of that. And the variance of Navla QT, so this is what? This is just differencing it one time. And this is differencing it twice. So you see that it was 0.6 and now it's becoming 0.8, right? So you know that you should only difference it once. So 11.9 will something be here, 0.6 here, and 0.8 somewhere there. So you know that this is the lowest one that you have, and therefore this is what you are concerned with. And this actually is known as turning point, but we'll have a look at that, again later soon. So that's how you determine your D and how many times you have to integrate. So sometimes you have these handy tables, but for other cases you might not. So for those kind of cases, you have to, rely on the graphs of ACF, PACF, and all those sort of stuff to check whether it's stationary or not, and then maybe try to differentiate. So try to take a difference and then say what's going to happen next and so forth. So this was our first step where we engaged into differencing our series. So now once we have differenced, we will know the value of our D here, right? And then I can rewrite my ARIMA model. And I can take those 1 minus B raised to D factors common out from the left hand side. And now what I have left with is the P and the Q. So now the second step is not exactly the second step, but I'm just writing it. So fitting an ARIMA model. And now is the task to figure out what is the value for this P and for. Have I started recording? Yes, I did. Okay, good. Yeah. So let us say, if I look at the ACF of an ARIMA model where neither of my P and Q are 0, what do you guys think it will look like?
Declining.
It will be declining, right? And if I look at the PACF, how will it look like? It will look the same. It will again be declining, right? So because I have my AR and MA processes, which if one of them have a declining ACF, the other one cuts off at 0. So which doesn't say, specifically, if you have an ARIMA process, neither of these P and Q are 0, just by looking at the ACF or the PACF, the sample ACF and the sample PACF, you cannot determine what the value for P and Q will be. So what is it that we can do? So there is nothing that you can do by hand or by manually. What you have to use is the computer, and there will be some commands that you can use and fit the distribution. So you can start, let's say, with a simple model like ARIMA 1,1, and then you decide if it's a good model or not based on what I'll tell you next, how to see if a model that you have fitted is a good fit or not. So that will amount to goodness of fit testing. And yeah, so generally what happens is, let's say you have AR with P and MA with Q. So you have a ARIMA with P, comma Q model. So the very first question that comes to your mind is, how many parameters should I have? So remember, we have n data points, and should our P plus Q be n, or should it be something like n minus 1? Because I know that the number of data points that I have, those many number of equations I can make, right? So sometimes what you can do is, you can also use method of moments with calculating those ACFs, and I'll show you guys that in a bit about how to estimate the parameter. But fitting the model actually comes with, first estimating the parameters and then checking whether those estimates give you the minimum error or not. But sometimes if you try to, have P plus Q equal to N, so if you want to, see, there is this trade-off again. The more number of parameters you take, the more accurate your model is likely to be. But the more number of parameters you take, the more risk you put in if any one of them is faulty. So that can amount sometimes to overfitting, and therefore you have something known as information criteria to check whether the addition of an extra parameter is worth it or not. So you will have two models and you will check the information criteria for both of them. One will have the added parameter, the other one will not, and then you will determine which one of those will have the least information criteria, and then you go with that model. So let me just write here. So when I'm talking about information criteria, there are so many of these, like BIC, HC, SC, and SIC, I think. So this is the one that we are discussing, but this is actually, so you have this different kind of information criteria that fit along with different kinds of time series that you are looking. But I think probably for the actual purposes, AIC is the one that we use. So that's given in the book. And this is, okay, keys, information criteria. So the lower the value for this, the better our model is. And the formula for this is log of sigma h squared plus 2 times the number of parameters you have upon n. So you see what's happening here? We want a AIC to take a lower value, right? So if you put in the number of parameters as n, this is the maximum that this fraction can take, and you're adding this here. This doesn't look like multiply. Nice. So yeah, that's a multiply. So you have 2 times x here, right? So you're adding a higher value. So this is going to take a higher value as well. And that is how you compensate for the number of added parameters. So you have to make this guy as lower as possible. But you know that if you keep on adding the parameters, sigma square will of course be lower, right? And the same is the case with the R square as well, the capital R square that you generally look at in the regression. So now, instead of just looking at the sigma square value, you add this as a sort of punishment for the number of parameters that you're adding. And that is how you balance the trade-off. And the lower the value of AIC, the better the model is. So select the one with lowest AIC. I hope that's clear. So the next step is very easy. Parameter estimation. This is the fun part. So when I'm talking about parameter estimation, I know that I already have with me the values of P and Q. So whenever you are looking for these AICs, you check for different values of P and for different values of Q, and the combination which will have the least value of AIC is the one that you select. So now you know the value of P, now you know the value of D, and now you also know the value of Q. And now the only step is remaining to identify the model exactly is the parameter estimation. So let us say if you have a ARIMA P, Q model. So I have a ARIMA P, Q model, and I can rewrite my model as, so this will go until P, and then you have ET, and then for MA, you will have beta 1 ET minus 1, so and so till beta Q E T minus Q. And when I'm talking about the parameters, my parameters will be this alpha 1, alpha P, beta 1, beta Q. So these will be my parameters. You can also put alpha 0 here and beta 0 here, which of course take the values 1. But these are the parameters that now we have to, estimate. And the very first assumption that we make is that our error terms follow normal distribution 0, sigma square. And that is what, will allow you to even say that if you estimate the parameters using least squares or the maximum likelihood, they'll give you the same answers. But in general, they need not be the same. But if you have errors which are normally distributed, then they will have same answers for the estimated parameters. So I think we all are already aware of what happens if you, let's say, only have an AR model. So let's say to start off with, I have a ARP model. So I looked at my Z T minus 1 till this, right? And what I will do is, I will try to minimize the error that I have here. So I can just rearrange this equation and I can write it as ZT minus alpha 1 ZT minus 1 minus which is equal to ET here. So I will try to minimize my sum of ET square. So I will just sum it across and square it. So ZT minus alpha 1 ZT minus 1 minus till alpha P ZT minus P square, and summation again will go from P plus 1 till N, and we denote it by T. So you choose the parameters alpha 1 hat, alpha 2 hat to minimize this equation here. Is that good? So remember, when I'm using a least square method, I'm not putting any distributional assumption that my error term can follow. I'm just writing my error terms and summing them across all the t values and squaring them. So I've rewritten my error terms in terms of the z's and the values. So these are small z's, the value that this random variable takes. And now I'm just summing them and squaring them. And I'll try to minimize this. So in turn, you will differentiate and all sort of stuff. And I'm sure you are already aware of, how the least squares is carried out. So that's how you will estimate a AR process. And so now what happens is, if you have a positive value for Q, if your Q is not 0, then there is some difficulty and you cannot possibly figure out manually what the answer is going to be for these parameters that you want to estimate. So let us say you have ARIMA model. So let us say you have ARIMA model 1,1. So previously the thing that we just did with the least squares was AR with P. There was no Q, it was just 0. So now if you are looking at ARIMA 1,1 model, you can rewrite your error term as something like ZT minus alpha 1 ZT minus 1 minus beta 1 ET minus 1, right? So what happens is, you are trying to solve for ET, You do not know ET as of now, but in turn to figure out the value for ET, you need to be aware of what value ET minus 1 takes, which might not be the case always. So what you have, because let's say if you're predicting something 2 steps ahead, then you also don't know what's going to happen next, right? Because you're only at today and you only have the information which is up until today. So what you can do is you can assume some value for ET minus 1, and then you figure out the value of ET on the basis of that. And there is some judgment involved from the statistician's part to see what should the starting values be, but sometimes it's just easier to start off with 0 because these are the error terms. So you start off with 0 and then you see what the values of alpha I, alpha 1 and beta 1 suits, and then once you have the model in place, you try to fit in with the data, and then you will get some residual values. So you will see and figure out the difference, and on the basis of that, you will update your new values for this error terms. And then those new values will again be used as the starting point for again going through the whole process, So these new values of error that you get will again be put into the model. So let's say you had this model, you assumed some value for ET minus 1. After assuming this value for ET minus 1, you got some value for ET, right? And you got the values for alpha 1 and beta 1 as well. So now that you have alpha 1, beta 1, ET, you can easily model this whole thing and figure out the value for the error term. And once you have that error term, you update that again and you put that again in the equation and you get some another error term. And you continue doing this until you get the value of the error term which you substituted initially, the same as the one which you get at the end once you model the once you put in data with the model that you have estimated. So I think I can maybe summarize it again in case this was confusing. So what you have is you start with some values of ET minus 1 and ET, and you try to use these values to estimate the beta 1 and alpha 1 here. So you do not have to use this information as of now. You just have to square this and minimize it to get to a particular value of alpha 1 and beta 1. Okay. Now you have these values of alpha 1 and beta 1. And now you write this model exactly as it is. You just substitute the values of alpha 1 and beta 1 here. And then once you substitute the data that you have, you will get the values for ET and ET minus 1 somehow. And then you check whether the assumed values of ET and ET minus 1 previously are equal to the ones that you have gotten now. And if those are equal, then you have successfully back forecasted your model and the parameters have been estimated correctly. But if it is not correct, then whatever at the end value you get for these ETs, you use that as another input in assuming that this is the value that your ET takes, and then you again recursively go on, repeating this technique again and again iteratively until you converge to the same values of E that you started off with at some point. So this is one method, and the other method that you can do is something like, if you have, this is actually not that easy as well, but sometimes if you have P plus Q as not a higher number, and for computer, I think nothing's that difficult until unless you have something which is beyond its computational ability. So you can just use those ACF equations to figure out, and you can have, let's say, P plus Q ACF equations, and then what you will have is these values R1, R2 till Rp plus Q, and you will have these values and you will also have the equations, right? Just the way we used to do that previously, and then you can estimate the parameters easily. Let us see an example of how is this being done. Yeah. Yeah, so this is actually a case where they show, that if your E is normally distributed, then the maximum likelihood estimation is equally likely, to minimize the squared error. So that's essentially the same thing. Um, yeah, but this is what we are looking at. So now we have something. Yeah. So now what do we have? We are asked to believe that there is a set of data values which is realized from MA1. And the process is something like this, as likely MA1 would be. So the errors are standard normal, check. And then they have given us these sample values for the ACFs. So ACF for 0 we know is going to be 1. And so not necessarily it is 1, but here it is 1. And for this lag 1, we have minus of 0.25. And we are asked to estimate the parameter beta, ensuring that this is invertible. So again, we have to, not forget the root cause of root base of, the use of these kind of models to forecast is that the processes should be stationary. So now you figure out the row 0 value and row 1 value using whatever we had at hand. So this is the model that you have, and you substitute it again, and you know that here you will just have this and that. So this will amount to 1 and this will amount to beta square because these are standard normal. So the variance is just 1, and that is why you just have 1 plus beta square here. And for gamma 1, you get beta. So now you know that row 1 and row. So now you know how to figure out these values for row, and you just substitute this beta upon 1 plus beta here and beta upon 1 plus beta square here, and you figure out these values. So again, just by simultaneously solving these equations, you get that the value for beta can either be this or that. Because it is a quadratic equation, you have these two values. But we have to make sure, that the process we have at hand should be invertible. So this beta should be less than 1 because I know that that beta is something which is on the right hand side. So I haven't yet inverted it. If I would have inverted it here, then I would have required the roots to be greater than 1. But now it's as it is where it is. So it should just be in absolute terms less than 1, and this would be greater than 1. So this is the 1 beta that we have estimated using method of moments. And I hope that's clear. So yeah, the next step that you can do is, so now that you have figured out the parameters, which are alphas and the betas, the coefficients of x's and the e's that you have. The final parameter is sigma square, and which is as we know the variance of 18. So the very best guess is just to approximate it with this. So sigma square is denoted by this. This is no surprise that we again start off with p plus 1. But yeah, and that is how you will calculate the sigma square. So yeah, we have to, actually realize that this sigma square has not been used to estimate the other parameters. So here you would, be surprised to see what happens. Actually, not even surprised. I guess you guys must have expected that this is going to happen. Let us say instead of standard normal, I just have normal. So I have 0 comma sigma square here. So my variance here would be what? My gamma 0 will be sigma square plus beta square sigma square, which is what? This, right? And here I would have beta sigma square. All right. And now if I have to figure out my value for row 1, what will it be? It will just have some sigma square here and sigma square there, which would cancel out. So in effect, I'm never using my sigma square to determine the coefficients. to estimate, to estimate the parameters that I have as yet, right? And that is why it doesn't hamper the process, even if you don't have a standard normal distribution and just a normal distribution. So yeah, I guess that's it. And now we will look at diagnostic checking.
Ma'am, did you say that in case of normal, it won't depend on sigma square?
Yeah, the coefficients that you estimate.
But but that was not, the sigma square was not actually getting cancelled. It was coming to sigma square beta upon 1 plus sigma square beta square.
Oh, wait. Let us do that again. Okay, I actually mistakenly wrote that as wrong. So what you will have here is 1 plus beta square sigma square, right? Because the answer that I would get is for ET, and ET will be sigma square. And here you will have beta square sigma square. So I take sigma square as common and I'll get 1 plus beta square. And for this guy, I will have beta sigma square. So this and that would cancel, I mean inverse here.
Yeah, okay.
That was a good catch. Thank you very much. Great. Very good. So, yeah. Okay. So we have 20 minutes left. Yeah, it's doable. So let us start with diagnostic checking now. So now we have identified the model that we have, and we have also estimated the parameters of our model, right? But what's the guarantee that the model that we have estimated is indeed the correct one, is indeed the best one that we can have at hand? So this is where diagnostic checking comes into place. Okay, and there are again certain methods, to check. And the very first one of them is that if you have a model, once you have approximated a model, then the residuals should be an approximation to a white noise process. So the very thing that you will check is the fact that your ET hat is a good approximation to a white noise process. So we have already looked at, a couple of tests like portmanteau and other methods to see if the confidence interval one, to check whether our ET has any correlation or not and determine if it's a white noise or not. So the first thing that you can do is, instead of using an equation or anything, just plot your residuals. And maybe while plotting, if you recognize that there is some pattern, then it would suggest, that there is non-independence and there is some dependence in the error terms that you are looking at. So if you're, so the first method would be to inspect the graph of ET. Okay, and I think even if you plot a line chart, you can see a pattern, or if you plot something like a histogram and you see the distribution of the graph, you can more or less see if it's normal or not, or maybe just impose a normal distributions line graph or the PDF on that model with the same mean and the same variance that your error terms have. So that would be first. And the other thing that you can again do is check the sample autocorrelation function. So the next method would be to check sample autocorrelation function of ETs. So again, remember why I am writing hats, because these are the values that I have, observed in the data. These are the estimates that I have for my AT. So again, if I want to check, I can just, check my sample ACFs, and I would expect them, ideally, in ideal case world, I would expect them to be 0 everywhere, but they wouldn't be, I know that. So I have some confidence interval, and I'll make sure that they do not lie outside that range. So again, I can use my young box statistic with these. So yeah, I can use any of these methods, and that's good to go basically. So the third method that we have is counting turning points. Does anyone know here what is a turning point? Has anyone heard the term turning point? Maybe while you were learning differentiation or something.
Is it when the values, if they're going up, they suddenly go downwards and then upwards? So it's sort of a turning point.
Yeah.
In that.
It is exactly that. So what I say is a turning point. It is indeed a turning point where if there was a downward trend, it suddenly goes up, or if you were coming, or if you are going up, you suddenly, start going down. So in terms of mathematics, you can, write it as if my value at k minus 1 was lower than my value at k, but now my value of k is higher than my value at k plus 1. So what I am looking at here is that my yk plus 1 is here, and my yk was somewhere there, and now my yk plus 1 is again somewhere here. So I have this. So this is my turning point right here. And again, it could be like this, or it could also be like this. So you can also write it as the fact that your this is greater than this, but now your yk is less than yk plus 1. Sorry, yk should be greater. So yeah. So k minus 1 is greater than yk. Now my yk should be less. That's correct. And my yk is less than yk plus 1. So you can have this sort of things, but let's see how to use this, turning points method, and what does it actually help us to say. So the number of turns that your data takes. Let's say, have you guys heard of mean reverting process? So if you have a mean reverting process, I know that if a value today is much, much higher, then I know that to come back to its mean, because it is a mean reverting process, which is going to come back to its mean, I know that it is going to take some very, very low value to make it, stabilize the mean. And that is what is the crux of this counting turning points method. So what happens is, in any white noise process, you have some expected number of turning points, which of course depends on the number of values you are looking at. So it is something like this. And you have the variance for this guy, which is 16n minus 29 upon 90. You do not have to worry about from where these were derived, but yeah, it's expected that, if you are looking at a white noise process, then the mean turning points should be close to 80. And it should neither be too far nor too small. So it should be, and the variance also should be within the limits. So now you can say that if you have a very large number of data n, then what you say is, you say that your t here, so the turning points follow normal distribution with expectation ET and variance VT. And now I guess you all are aware how I can conduct a test. So in the case of young box statistic, I know I'm looking at a chi-square. So I'm looking at a right tail, which is a one-sided test. But now I'm looking at a two-sided test. So my test statistic here will be something like t plus or minus 0.5 minus expectation of t upon the square root of variance of t. And this is likely to follow normal 0, 1. And then you can, conduct a two-tailed test where, so again, when I'm writing here, t plus or minus 0.5, it depends on when you should take a plus and when you should take a minus. So if my value of expectation of t is higher than t, you should take plus 0.5. And if your expectation of t is lower than t, then you take 0.5. So that is just adjust. And now we know that if and only if my test statistic, let's say if I'm looking at 95% confidence interval, minus 1.96, and here I'll have plus 1.96. So if and only if it is within this interval, you will have insufficient evidence to reject H0. So you can say that errors form a white noise process. Maybe I should set the H0 here. So my H0 is that my errors follow white noise process. Okay, this is important. Is this clear to everyone?
Yes.
Okay, so again, you have to remember that this result is only for an independent sequence of random variables, which we know error terms are, and therefore you can apply this to the residuals of the time series that we have. And again, there is this one fact to be considered that this can only be applied to the residuals of the time series, not to the original time series itself, because in the original time series we know that there will be dependency between ET and ET minus 1, and those will not be independent. So there might be some bias in the process. And I guess that's it about the diagnostic tests. The next step is directly to forecast. And we have 10 minutes, so I think we can maybe do the basics of forecasting, and then we'll need one more lecture, to do the rest of the stuff. But yeah, so let us start with forecasting now. So now what we have done as yet is we have identified the P, the D, the Q. So we have in essence identified the model that we're looking at, and then we have estimated the parameters of the model. And now we have also checked whether the model that we have fits good to the data and to the expectations of ours from a good time series model. So the next step is to use the very purpose, to use this model, for the very purpose that we created this model for. So that's forecasting. So let's look at forecasting. So again, there is, this is in continuation to the Jenkins approach to forecasting this time series. So what you have is, let's say we start off with the ARIMA model, 1,1 model. Let us see, how do we write FA fork. So there is some notations that you will have to use, and it takes some time to get used to. But I think if you will practice, that's very easy. So if you have a ARIMA 1,1, I can write my model as xt equal to mu plus alpha times xt minus 1 minus mu plus beta et minus 1 plus et, right? And now I want one step ahead forecast from t. So what I want is one step ahead forecast from T. So essentially what I'm looking for is xt plus 1. And if I were to write it, I will get something like xt minus mu plus beta et plus et minus 1. I think this should be 2 plus 1. Yeah, et plus 1. Okay, so the very first step that you use is you will replace the unknown parameters with their estimated values, which you have, just estimated in the previous steps. So replace all the unknown parameters by their estimated values. So what will you get here? You will have xt plus 1 will be equal to, so mu will be estimated. Then you also have estimated alpha hat. Then you can have xt here minus mu hat plus beta hat et plus 1. So this is the first step. The next step you do is to replace all of these random variables by their realizations. So here you only have one of these. So you replace all the random variables x1 here, sorry, xt here with their observations. So what will I have here is mu hat plus alpha hat small xt minus mu hat plus beta hat et plus 1, right? Cool. So again, the next step is to replace the random variables that we are looking to forecast with something that I'm going to write now. So let me just write it as xt plus 1 here, xt plus 1 here. So replace the random variables xt plus 1 here. So if you have more variables, this will all be variables by their forecasts value. So here, because we're looking only at, xt plus 1, this will be the only thing that's going to alter now. So what you will have is, instead of xt plus 1, you will have something like xt and in this bracket 1, which denotes that you're going one step ahead of xt, which is xt plus 1. And the rest of it will be as it is. Okay. And the next step will be to replace the e's that you have. So replace the innovations that you have. So you replace the innovations. So here you only have et, right? You only have et plus 1 here, I guess. So you only have et and et plus 1 here, and you already know the value of et, which you substitute so you know the realized value will be et hat. So what you will write here is my xt1 is mu hat plus alpha hat xt minus mu hat plus beta hat et hat plus et minus plus et plus 1, right? So the next step will be now to replace the random variables, the innovations which you haven't yet realized, with their expected value. So I will replace the random variables en plus 1 by their expectations. And what is my expected value of E? It's always 0, right? So instead of t plus 1, I will just have a nice 0. So these are just a couple of steps that you have to take to forecast, and to write it in terms of, this is very, I feel like this is just a very tedious process and not so much of importance, I would say. But yeah, it's what you got to do. But I think, so now by doing this, you have a value for, so remember again, the forecasted value is also this. So at the end, you will be left with xn1 hat. And this is also the value that you're estimating. So let me just walk you all through the process again. So remember, we started off with a model for which we wanted a one step ahead forecast, right? And now what we do is we first replace all the unknown parameters with their estimated values. And then what you do is you replace this xt with its observed value. Then you realize that the thing that you are going to forecast and the stuff that you don't know about yet, you write them in terms of xt. So if you would have had, let's say, xt plus 2, it would be xt in bracket 2. And then you replace the innovations which you know about, which you have estimated already as with their realized values. And at the end, you write the values that you have to forecast, and you write their expected values in the place of the actual value. So I hope that's clear. And let us now I'll just walk you guys, through one example now. So it's not going to take much time, I would say. Yeah. So if you were to write a two-step ahead forecast for an AR2 model, it would look something like this, right? So let us see in the actual model, what would we have? So I want to figure out xt plus 2, and I have a AR2 model. So what I would have, its mean. So I'm not writing that as of now. I will have alpha 1 x t plus 1 minus mu plus alpha 2 xt minus mu. And if you are to write it in terms of, the forecasts, so you write everything in terms of xt. So now they have used n, but it doesn't matter much. So you're writing x hat n 2 because you're essentially looking at xt plus 2, and the bracketed term is the step ahead that you're looking at. And mu will be replaced with its estimated value, alpha 1 with its estimated value, and the same goes for the rest of them. So like, see here, you have x at n 1, which is xt plus 1's estimated value, and here you just have xn. So I hope that's clear. And yeah, they have just again asked you to write the step for ARIMA 2,2. So here you have to, be careful. Whenever you have this MA process, now you have QS2. This is your Q, right? So remember, the only value from MA that will show up in the forecast is the time from today's. And all of those values, which will have en plus 1 and all of those will be replaced with their expected values, and those will become 0 eventually. So it won't matter at the end. Yeah, so it's essentially, just saying that the step ahead forecast, you are taking conditional expectation of all the future values depending on all the information that you possess up until time today, which is N. So yeah. Oh yeah, and again they have this, again some sort of discussion about the way you forecast. So the forecasted value can be either a point estimate or a prediction interval. So this is where the prediction interval term will, suit much better. So the very first thing you have to know is to make these intervals appropriate ones and even accurate ones, what you have to assume is that the residuals are uncorrelated and normal. So only if both these are true, which you can easily check, by just plotting a ACF or a histogram of the residuals, you have to make sure that these are uncorrelated and normal. So then what you can do is you can have a prediction variance and the prediction interval based upon that variance, which will give you, not a point estimate, but a whole set of values that your forecast can take. So I think you guys must have seen, if you guys must have seen, the inflation reports or any stock price data being forecasted, sometimes you see a fan. So let's say this is what has been happened up until now. And what will happen next is you see a fan of these events, So if these are the ones that you are trying to forecast, then they will give you some like this. And so let's say at this time, if you are forecasting, the parameter can take, the variable can take any value in between this. So they have this intervals, and this is what the interval will be. And if you only look at a point estimate, it will give you something aligned like that. So that would be for point estimate. And if you have a fan like that, it would be for the interval. I don't know what that is. Yeah, and they haven't written interval anywhere. So you will figure out this prediction intervals for the models that you have as the forecast horizon increases. So remember, when I'm talking about my forecast horizon, it starts from here. So all of this is my forecast horizon. And as and when you increase, you see that it is more likely that the variance will increase, because the more steps ahead you are trying to forecast based on the information that you have up until today, the lesser and lesser sure you will be of that value, because this value also depends on this and that, which you do not know any of yet. So generally what happens is in ARIMA models, this is not as wide as in the other models. So you might just, observe something like this. It is a bit narrower for the case, and it's, in a way, a good approximation as well, because they say that the error in the variance. So, okay, the error which is there in the variance is already accounted for, but there are some other errors which are not accounted. So the parameter that you have estimated and the model order that you have, P and D, those might have some flaws. So the error from those will still be there. Only the variance in the error has been accounted for. So it will have a narrower range, and it is said that, as and when you increase, it will converge for large values of K to gamma 0. So that's also the case, and that is how, you forecast, you write the forecast, and you can either use a point estimate or an interval. I think intervals are the thing which you should go for always. So now in the next class, we will look at the rest of the chapter, and I think that's it for today, until unless someone has any doubts, you can ask. Now I have 2 minutes. Any doubts?